In this video, we're going to cover section 1.6.2, the steady state approximation. Let's consider the following sequential reaction, similar to what we saw in the last video, except for now we have two intermediates. So we have the species reactant A decaying to give you intermediate 1, which then further transforms and decays into intermediate 2, and then intermediate 2 finally transforms to our final product. So in this reaction, product formation results from the formation and decay of two intermediate species, I1 and I2. So if we're to set up the differential rate expressions for the various components in this scheme, we would do so in the following manner. The rate of the formation of A, our reactant, will be equal to a minus K1 times the concentration of A. The formation of intermediate 1 is dependent on the decay from A and also its own decay to A2. And so the formation of I1 is dependent upon a plus K1 times the concentration of A minus a K2 times the concentration of I1. And recall, we can set up these expressions, these rate expressions, because we know these are elementary steps in our reaction mechanism. So the molecularity of that step can be easily discerned. Similarly, the differential rate expression for the second intermediate, I2, can be shown as follows, where we have the rate constant K2 times the concentration of I1 from which it decays, as well as when I2 transforms into the product, we can designate that with the expression a minus K3 times the concentration of I2. And then finally, the differential rate expression for product formation is equal to K3I2, because this is the only path that leads to the formation of that product. So very similar to what we saw in sequential first-order reactions, except now we have an additional step within our scheme. We have 3 steps and 2 intermediates. Now it is possible to determine the time-dependent concentrations for the species involved in this reaction by integration of those differential rate expressions. However, this is not trivial numerically. So we've seen previously for a one-step reaction or even a two-step reaction mechanism that we can solve for those individual concentrations numerically. As we increase the number of species in our reaction mechanism, though, this becomes more complicated numerically or mathematically. So the question we must ask ourselves is, how can we determine the concentrations of these individual species if numerical solutions are more challenging? One approach is to use the steady state approximation. This is used to evaluate those differential rate expressions by setting the time derivative of all intermediates approximately equal to 0. And we can do this under the approximation given that intermediate concentrations generally change very little with time. So the expression we use to indicate that we're applying the steady state approximation is shown, where we will state that the change in the intermediate concentrations with time is approximately equal to 0. We show it equal to 0 in this particular example. This approximation is particularly good when the decay rate of an intermediate is greater than its rate of formation, so that as the intermediates are being formed, they're decaying or transforming into the next species very quickly. And so as a result, those intermediates are only present at very small concentrations during the course of that reaction. And so here's a pictorial view of what we're assuming with the steady state approximation, is that we're assuming that, yes, there is an initial growth of the intermediates as a result of the decay, initial decay of the reactants, but during the course of that reaction, that the concentration of the intermediate is quite small relative to the concentration of reactants and products in that same reaction system, and that it's relatively constant. You can see that the slope of this curve, if you will, or of this decay is quite constant during the course of the reaction. And so this is the basis for the steady state approximation. that the concentrations of the intermediates will remain small and that they won't change very much during the course of that reaction. So how do we go about solving for the product concentration when invoking or implementing this particular approximation? Well, let's apply the steady state approximation by setting each of those intermediates in our reaction scheme to 0, or the change in the rate of formation of those intermediates. So if we do so for intermediate 1, so if we take that the net rate of change of intermediate 1 with time, if we say that is equal to 0, that's taking those two terms in our rate expression and equating those two terms to 0. In doing so, we can now solve for I1 in terms of the concentration of A and the rate constants responsible for those two steps. And so you can see that the concentration of intermediate 1, when we rearrange this expression, will be equal to a ratio of the rate constants K1 over K2 multiplied by the concentration of A. And so we've seen previously that A to I1 being a first order reaction, that the molecularity is well known. We have a single molecule of A being converted into intermediate I1. We can then substitute for the concentration of A with our integrated rate law expression for A, which is A is equal to A naught e to the minus K1t. And so the net result is that this equality results from the integration of the differential rate expression for A, as we've seen previously, where we have those initial conditions that the concentration of A initially cannot be equal to 0, and that all the other initial concentrations, that is I1, I2, and the product, are equal to 0. So nonetheless, what we've done by implementing the steady state approximation is we've been able to solve for the concentration of I1. Now we can apply the same approximation to any other intermediate in this particular system, and we'll do so for I2 now. So the net rate of change of I2 with time, we're equating that to 0 under the steady state approximation. Again, we can equate that to the two terms which we use to express the change in that concentration with time, both with respect to the decay from I1 and the formation of the product from I2. In doing so, by using the steady state approximation, we can now solve for the concentration of I2, and we see that I2 now is equal to K2 over K3 multiplied by the intermediate concentration, intermediate 1 concentration. Now we just solved for the concentration of intermediate 1 by applying the steady state approximation for that intermediate species, and we just solved it as the following term that we ended up with K1 over K2 times the initial concentration of A multiplied by the exponential to the minus K1t. And so we can carry out that substitution, and as a result, we end up with a solution for I2, where the rate constants K2 will cancel in our final expression. So now we have solutions for I1 and I2, and as you can see, mathematically, we haven't had to use any complex integrals to solve for these particular concentrations. So now we can take this information, and what we're after is to be able to evaluate the product concentration through time, or as the reaction proceeds. And so the product concentration, the change in the product concentration with time, we saw that that was equal to K3 times I2. We now have a solution for I2 by using the steady state approximation. And so we end up with the following substitution, and we have further simplification where K3 will cancel in that substituted expression. And that leaves us with our final expression in which the rate of product formation is going to be expressed in terms of the reactant, the initial concentration of the reactant A. And so we end up with our final expression where K1 times the initial concentration of A and our exponential term e to the minus K1t, this can be used to determine the net rate of change of the product with time. So now we have a very simple expression that we can integrate. So if we now integrate this particular differential expression, we're going to find that we're going to end up with our common expression for the concentration of product like we've seen previously. But let's go through the integration where we rearrange the expression, bringing dt up to the right-hand side. K1 and A naught, these are both constants. And so what we're left with is solving the expression e to the ax. That is the form of the integral that we need to solve. And so the solution to that is 1 over a e to the ax, as you may be familiar with. And so here is the final solution. We have the product concentration equal to our constant. We're then going to have our solution minus 1 over k1 e to the minus k1t, our limits being t and 0. This term is going to simplify where e to the 0 is equal to 1. Okay. So we end up with a product of k1 a naught bracket minus 1 over k1 e to the minus k1t plus 1 over k1. And we can do some rearrangements where we can factor out the 1 over k1, and then that will cancel out with the k1 out front. So we're going to see cancellation of these terms. And so what we're left with is, as shown, we end up with our product concentration equal to the initial concentration of A multiplied by this 1 minus exponential term, e to the minus k1t.